Welcome back. I'm going to start with reviewing what we covered at the last lecture. So we were comparing the simple harmonic motion to a free-fall motion. And I introduced the potential, which is quadratic for simple harmonic motion, and it is linear for the free-fall motion. For the simple harmonic motion, the force is proportional to the position. That is, I have some equilibrium position x0, which is sitting around here, and the force is then proportional to the deviation from that equilibrium position. And from the Newton's law, F equals ma, one can then derive this differential equation, which relates the second time derivative of the deviation to the deviation itself. And we define this coefficient here, k over m, as the angular frequency omega square. And the resulting motion looks like a sine or a cosine, as shown here, as a function of time. So this is time, this is position, and it oscillates around this equilibrium position x naught. And one can define an amplitude of the oscillation, which is the maximum deviation from the equilibrium, and a period, which is the distance from crest to crest or trough to trough. And then omega equals 2 pi times the frequency, or 2 pi divided by the period. So the frequency is inversely related to the period. So mathematically, we describe this as x equals x naught plus a cosine omega t plus an angle phi. And the velocity is the first derivative of this. So the cosine becomes a minus sign, and the phi doesn't come out. The omega is transported out, and I get v equals minus 8 omega sine omega t plus phi. So the maximum velocity is the amplitude times the frequency. And then one can do the same game again and get the acceleration. And the sine becomes again the cosine, and the maximum acceleration is minus a times omega square, or minus a times k over m. One can then assume initial conditions. At time equals 0, there's some initial position xs and some initial velocity vs. And then simply plugging in those equations, we get that a cosine phi must be equal to xs minus x naught, and a sine phi must be equal to minus vs over omega. And these two equations are sufficient to determine phi and a in principle. And to do that, one uses a little trick. One exploits that cosine square phi plus sine square phi equals 1. So if we square the first equation and the second equation, then we get this relation that a square equals xs minus x naught square plus vs over omega square. And the division, the ratio of those two equations, relates the tangent of the angle to xs and vs and omega. So so much to as far as the review is concerned. You have a question? So what we didn't cover last time is the energy of the simple harmonic motion. And one component of the energy we already have, and that is the potential energy, which was this quadratic function that I just erased. This quadratic function is the potential energy. And then the kinetic energy of the simple harmonic motion is just like kinetic energy always is. It is 1/2 times the mass times the velocity at that instant. So for the potential energy, we get 1/2 kx minus x naught square. And plugging in the formula for x minus x naught, which is a cosine omega t plus phi, we get then 1/2 ka square cosine square omega t plus phi. And so for the kinetic energy, it is 1/2 m times the velocity square, which is 1/2 m a square omega square. As I just told you, when getting the velocity, the cosine turns into a sine and the omega gets transported out. So v equals dx minus x naught dt, which is d dt of a cosine omega t plus phi so this is where these factors a squared times omega squared comes. It's squared because the velocity is squared. And since we know that omega squared is k over m, that means that m times omega squared must be equal to k. And so I get 1/2 ka squared sine squared omega t plus phi, which looks very similar to the potential energy, except the cosine is replaced by a sine. So one can sort of follow the simple harmonic motion and look at, like in this graph, and look at how the interplay happens between potential and kinetic energy. And for example, here, the particle is at rest, the mass is at rest, velocity equals 0, so there's no kinetic energy, and it's all potential energy. Then the mass gets released, it travels to x equals 0. At x equals 0, there's no potential energy at all. And the energy is all kinetic energy. So u equals 0 and k becomes maximal. And then the mass slows down and reaches the opposite point. The velocity again is 0, and we have the same situation as here. And then it travels back, and for example, to some distance x, and there's some potential energy and some kinetic energy. Of course, the total energy is the sum of the potential and the kinetic energy. And using again this relation, sine square, cosine square plus sine square equal 1, if we add those two equations, we just end up with 1/2 ka squared. And that happens to be the same as 1/2 the mass times the maximum velocity square. And again, the maximum velocity is a times omega. And of course, k equals m omega squared. So to reiterate, we can relate theta to omega t, and so omega is an angular velocity, and the projection of a uniform circular motion is a simple harmonic motion. So far we have represented our simple harmonic motions by using springs and the mass on the spring. But one can actually use something far simpler. So here, for example, I have a lead weight, and if I suspend it like this, and if I sort of deflect it a little bit, as long as the deflection is small, the projection on the floor is actually a simple harmonic motion, just like for the spring. So if we make a sketch of this, so here is the lead weight, that's the string, it has some length L, and we deviate it from the vertical position by a small angle theta. So because this is a perpendicular triangle, this projection x is L times the sine of this angle theta. And now we are doing another little math trick. We assume that sine phi is approximately equal to phi. And this is a fairly good approximation as long as phi doesn't get too big. And by the way, one can make a similar approximation of the cosine of the angle. And to the same quality, this equals 1. So if you want to know how good this approximation is, you can also simply look at how close is the cosine of the same angle to 1. So if we do make this approximation, then the tangential force, which is the restoring force going in this direction, it splits up from the force of gravity. This is the force of gravity. And this is the restoring force. And this is the force that suspends the, the mass from the string. So that sort of keeps the string taut. So this is the cosine of theta, because this is the same angle theta here, from here to here, as this one. And we don't need to worry about this one as long as it's not big enough to tear apart the string. So the interesting one is this tangential force, mg times sine theta, or when I make this approximation, mg times theta. And as for the mass of the spring, it has a minus sign. So, and the minus sign is because it actually restores the mass to the equilibrium position at the bottom here. So since F tangential equals minus mg over L times x, since I'm calling this x, which is L times the angle. Yeah, this is this equation here. This is simply the definition of an angle. Let me remind you about that the way the mathematicians define an angle is they make a unit circle. And this is the angle theta. And they say this distance here, that is the amount of radians for that angle. So when you go all the way around, it's 2 pi. And therefore, theta is simply this distance x divided by 1, since this is a unit circle, or more general, x divided by the radius. So if I look at this equation, F tangential equals, or approximately equals, minus mg over L times x, then it looks like the force for the spring, where the spring constant is mg over L. So we can basically use what we had before, except that we replace the k with mg over L. And then instead of omega square equals k over m, it has become simply g over L. And we can try this out. So let's look at my pendulum here again. So sort of remember the period. If I halve the string, then the period becomes much faster. And actually, one could use such a simple device to measure the acceleration of gravity, because all I have to do is measuring this, the length of this pendulum, and because of this equation, if I measure the frequency with which it swings, it tells me how big is g. So there's also a different type of pendulum. And for this pendulum, we have assumed that all the mass is concentrated at the bottom here. So we assume that the string doesn't contribute. One doesn't have to make this assumption. You can take any odd-shaped object and it becomes a pendulum in the same way. And it also seems to be a simple harmonic motion. So how does that work? So first of all, my apologies for a computer font problem. What I meant to say is that the torque equals the force times the lever arm. So let me write it down correctly here. So this is actually a vector equation. But if you don't like cross products, like most people do, then you can simply calculate the perpendicular distance, where you take into account this angle theta, and then the torque actually becomes the force times this perpendicular distance. So this perpendicular distance is h times the sine of the angle theta. So h is the distance between the center of gravity and the point of suspension. So, by the way, one can treat the baseball bat as a pendulum. And in fact, one probably should if one wants to play baseball efficiently. So now we are doing the same trick for this obnoxious sine theta that appears in the formula. We simply assume that theta is small, and therefore the torque becomes mgh simply times theta. Now we use Newton's law for rotation, which says that the torque must be equal to the moment of inertia times the second derivative of the angle. And if we do that, because of this equation, we again get the equation of a simple harmonic motion. Second time derivative equals some factor times the quantity itself. And if we define this quantity here, which is the moment of inertia divided by the mass times this distance h, and I will call this the reduced length, and it'll become apparent why in a moment, because now I can take this this equation here and I can write it as d square theta dt square equals minus g over L star theta. So now the equation looks exactly the same as it did for the simpler pendulum. The only difference is that instead of a simple length, I have this reduced length, which is not so easy to determine. This reduced length is not simply the distance h. So I can't take the physical pendulum and find the center of mass like this and say this is my reduced length. It actually depends not only on the shape of the object but also on how the mass is distributed. So if this part is more dense than that part, then it will change. However, qualitatively, the fact remains that it swings slowly for a long reduced length, and it swings more quickly for a shorter reduced length. Now, the simple pendulum we can use to measure the acceleration of gravity. Assuming we know the acceleration of gravity, we can turn it around and use a pendulum to measure the reduced length, and because of this formula, the moment of inertia. And I'll do this in an example. So this provides actually an easy way to measure the moment of inertia, which is not a very easy quantity to measure in general. So we can measure the moment of inertia about any axis that we wish. If we simply pivot it around the desired point and then measure the period of oscillation around that axis. So let's suppose, for example, that we have a 1 kilogram stick. And that 1 kilogram stick is balanced at a point that is 42 centimeters from one end. So we know that the difference between pivot and center of mass is 42 centimeters. And we also know that it oscillates with a period of 1.6 seconds when we let it swing around that pivot. Then what is the moment of inertia about that axis? And the answer is, we know that omega equals 2 pi divided by the period. And if you plug in the number of the 1.6 seconds, you get 3.92 per second. Or we can square it and we get 15.4 per second square. We can then use the formula with the reduced length and turn it around. So we have omega square equals G over L star. That means that L star is G over omega square, where we simply divide both sides of the equation with this factor. So if we do that, then we can calculate the reduced length as 0.635 meters. And we can then use the formula for that relates moment of inertia and reduced length to calculate what is the moment of inertia. So this is the 42 centimeters, or 0.42 meters, times the 0.635 meters. And it is 1 kilogram, so the mass is 1 kilogram. And if we do that, then we get the actual answer. So, oh, sorry, yes, you have a question?
Would you explain the concept of reduced length again? Would you explain the concept of reduced length again? I don't understand the L star.
Okay, I'll explain that again. Let me go back. So just to make sure everybody heard, he asked me to explain the concept of the reduced length again. So the idea is that we want to treat this complex pendulum like a simple one. And since the equations are similar, so one equation is d theta t square, or actually in this case, sorry, dx equals minus g over L x, and in the other case it's d square theta dt square equals minus mg h over I times theta. Therefore, I want to define a quantity for both of these expressions have g in it. So that part is nice, but the remainder, the mh over I want to think of it as just like a length. So I know from those two equations that mh over I must behave like 1 over length. And now, since this is not really a length, it's just a mathematical expression, I say this is a reduced length. And in physics, we actually do often such tricks where we find a formal equivalence of various problems, and then we define effective quantities like this reduced length. Let me now move on to damped harmonic motion. And there life gets really complicated. Unfortunately, when I take my pendulum and I wait long enough, especially if there's some friction involved, then eventually the motion stops. And we call that a damped harmonic motion. It is no longer a simple harmonic motion. And it is mathematically complicated. It depends, of course, how we assume the friction to behave. One of the cases that is actually treatable is if the damping force is proportional to the velocity. That means the faster the object moves, the more damping force there is. So since we know that the velocity is the first derivative of x minus x naught, then we simply have this coefficient b, which we call the damping coefficient. So now this equation, this type of equation that we had before, becomes more complex because it's not only that the second derivative equals minus some factor times this quantity itself, but there's also this damping force to consider. And that leads to this term that is proportional to the first derivative. And of course, the way you get this equation is F equals ma. So Newton's law still holds. The only difference is that now F is the restoring force plus the damping force. And if I divide this equation by the mass, and then I get the acceleration, then I come back to this equation here. So this is a nasty differential equation, because we can't so easily guess the answer as we did for the simple harmonic motion. And one possibility is to just know the answer and then sort of do the calculus and prove that it's the case. But there's actually a somewhat more elegant way if one uses complex variables. So let me make it clear, I don't expect you to be able to do complex variables in the exam or even in the homework problems. So I'm just going to explain it in terms of complex variables, because complex variables, even though they sound complicated, are actually not all that complicated. So the idea of a complex variable is that we have a part that is real and a part that is imaginary. And we assume there's a quantity called I, which when it's squared, it equals -1. And we call the first part of this the real part, the minus gamma. And the second part, without the I, we call the imaginary part, or omega prime. And both of them are just normal real numbers. And with such complexes, which is where the word complex variable comes from, one can calculate just with the usual rules. Addition and multiplication and so on work just as usual. For example, I'm sorry, this should have been in the second line. If I multiply x1 plus y1 times x2 plus y2, then I need to multiply this with that, and this with that, and the two cross terms, and I get x1, x2 plus I square y1, y2, and then the two mixed terms. And since I know that I square equals -1 by assumption, I get this expression here. So that, for example, is exactly how the multiplication of two complex variables works. And of course, the addition is even simpler than the multiplication, because we can simply drop the parentheses, and since it's just a plus sign that relates the complex. However, the real trick where it helps us for this problem is the so-called Euler relation, which is already several centuries old. So this is not cutting-edge mathematics. But the Euler relation is for mathematics about what E equals mc squared is for physics. It is really very important. And the Euler relation is, and I'm not going to even tell you why it's plausible that this is true. Just take my word for it, it's valid. So e to the I omega, for any real omega, is cosine omega plus I sine omega. In particular, if omega equals 2 pi, then cosine 2 pi is 1 and sine 2 pi is 0. So e to the I 2 pi equals 1. So if we use now a complex variable and say that for x minus x0, we're guessing the answer of e to the complex variable times time. And since I set it up like this, so I to the zt is e to the minus gamma t times cosine omega t plus I sine omega t. So this part is sort of what we want, either that part or that part. So if we actually want to relate it to something physical, we take the real part of this. And since this is a real number, this is simply e to the minus gamma t cosine omega t. So the way this function looks like, I mean, we will come back to this at the next lecture. I just want to show you the way this function looks like. This is an exponential function. An exponential function looks roughly like this. Let me make this bigger. And we multiply this exponential function. It's kind of like the amplitude of a cosine function. So it sort of looks like this. And here I've drawn it more beautifully with the blue curve. And it looks like that. And these are other solutions to the same equation, and I will tell you about it next time.